So, in the last class we basically looked at the stability of a first order closed loop system, where the forward amplifier has got is a single pole system. The nice thing about a single pole system is that the closed loop system is unconditionally stable, right. And we also said that we also discovered that the unity gain bandwidth of the forward amplifier also happens to be the gain bandwidth product of the closed loop amplifier, right. So, if you want more gain, more closed loop DC gain, then you will end up having a smaller 3 dB band, right. And I mean, this just happens to be to come out from the math, right, of a first order system. Now, people take this many times, people take this out of context and say, if you increase gain, bandwidth will reduce for any amplifier, right, and the gain bandwidth product is constant. These are like these commonly circulating myths that you will encounter, right, but that is not fully correct, simply because it happens to hold for when the forward amplifier in a feedback loop is a single pole system, and is you can easily come up with counter examples where this is not true, right. In general, you should expect that if you want more gain, you will get lesser bandwidth, but the fact that the gain times bandwidth is a constant, right, only happens when you have a first order loop gain, and the closed loop system therefore behaves like first order system, but otherwise in general it is not true. Now, what is the I mean, everything is nice with the first order system, except that there is a big practical problem. And what is the practical problem? You cannot get that A naught by 1 plus S by omega p, which is that what we used? S by omega naught, is it? What do we use for the forward amplifiers gain? Yeah, 1 plus S by omega naught. So, in the first order case, or basically one stage forward amplifier, the forward amplifier's transfer function is A naught by 1 plus S by omega naught, right. Unfortunately, in practice, this A naught cannot be very large in practice. And why do we need a very large A naught? Yeah, so basically the how well the negative feedback loop operates depends on how large the loop gain is. So, and the loop gain is basically A naught f by 1 over S plus omega naught. So, we would like that A naught f to be as large as possible, but unfortunately, if you use a single stage forward amplifier, then evidently there is not enough gain, right, and you have seen the reasons for that when we talked about these transistor amplifiers. So, a straightforward way of getting more gain is to simply cascade stages. So, basically we say, oh well, that is too bad, why do not we this is A naught, if I cascade 2 stages, then I have a forward amplifier which looks like this, okay. And please note again, at the risk of repeating myself, I will say that this is the need for a second stage in the forward path is simply brought out by necessity, right. Ideally, if I could get a very large A naught using a single stage, then all this discussion is a moot point. So, like everything else, the first thing we need to do whenever you see a feedback system, what did we do in the first order case? What are we trying to find? We want to find the input to output transfer function, and what is the first thing we will check with respect to the transfer function? We want to check if the closed loop system is stable or not, right. So, as usual VO by VI in the Laplace domain is nothing but 1 over f times 1 over 1 plus 1 over loop gain of S, which is the same as loop gain by loop gain plus 1. And what is the loop gain of S here? Well, it is straightforward, A naught square f by 1 plus S over omega naught the whole square, correct. So, VO by VI therefore is 1 over f times 1 over 1 plus S by omega naught the whole square by A naught square f, which is 1 over f times 1 over 1 plus 1 over A naught square f plus 2s over omega naught times A naught square f plus s square over omega naught square times A naught square times f. Now, what can we, so what term can we neglect in the denominator to make our lives a little less messy? Well, we say that, well, A naught square f, the whole idea in cascading 2 stages was to have a large DC gain for the loop gain, and therefore, A naught square f must therefore be a very large number. Consequently, we will be able to neglect that quantity, thereby resulting in a transfer function which is for all practical purposes 1 over f times 1 over 1 plus 2s over omega naught A naught square f plus s square over omega naught square A naught square f. Okay. So, first things first, first question, is this stable? This is the closed loop transfer function, right? The question is it stable? It is stable. Why? Well, it is a second order polynomial in the denominator, all the coefficients have the same sign. So, all the roots are in the will be in the left half S plane, right. So, the answer to that question is a overwhelming yes. Now, the question is, well, the left half S plane is a big place. So, the question a legitimate question to ask therefore is, where in the left half S plane are the poles located, right. And to do that, rather than work with all these multiple symbols, I will use a standard form of a second order denominator polynomial, which I am sure you have seen in different contexts. So, for example, I am going to write this as 1 plus s by omega p q p plus s square over omega p square, and this is what is called a standard form for a second order denominator. Okay. I am sure you have seen the similar standard forms in control, right, where they write it as some omega n square plus 2 times the damping factor times s omega n. This is what we like to use in circuit work, right, and for good reason, as we will see going forward. So, if you want to map this polynomial that we have, which is this guy here, to the second order denominator, standard second order denominator, what comment can we make about omega p and qp? What is omega p? It's very straightforward. It's omega naught times A naught times root f. Okay, and omega p qp, which is omega naught a naught root f times qp is nothing but omega naught a naught square f over 2, which implies qp therefore is nothing but a naught root f by 2. Does make sense? All right. So, let us now we mapped this the second order polynomial that we have for the denominator of our closed loop system to a standard second order system, right, and the closed loop poles of the standard second order system. Where are the poles located? Yeah, do the algebra, man. So, basically minus b is 1 over omega p q p plus minus square root of 1 over omega p square q p square minus 4 over omega p square over 2 over omega p square, which basically is minus omega p over 2 q p plus minus square root of I will take 1 omega p outside and another one inside the square root. That becomes 1 by 4 q p square minus 1. Correct? So, clearly as you can see, there is something under the square root. So, we will have to consider cases where the discriminant is is positive, it is 0 and negative. So, case 1 for qp less than half, what comment can you make? What comment can you make about that quantity there? It is greater than 0. So, you will have so what comment can we make about the location of the poles? On the very good. So, basically for q less than half, you have 2 poles on the negative real axis. Okay. All right. So, qp equal to half, the denominator will be a perfect square, and therefore, you have 2 repeated poles on the negative real axis. Okay. And finally, qp greater than half, you will have complex conjugate, and where are the poles located? It is minus omega p over 2 q p plus minus j omega p square root of 1 minus 1 over 4 q p square. Now, now I would like to draw your attention to this location of these poles, right. assuming they are complex. So, if I draw the complex plane, this is sigma and this is j omega. So, for exactly QP equal to half, where are the two poles? Minus omega. Okay, you will have two poles there. Now, as QP keeps increasing from beyond to values greater than half, what comment can we make about the location of the poles? The complex conjugate, of course, right? As QP tends to infinity, what comment can we make about the poles? They will be on the j omega axis. Where on the j omega axis? Plus minus j omega. Correct? Okay. For values q values greater than half, as the q tends to infinity, if you plot the locus of the poles, what will the locus do? Yeah, of course, it will break into two parts. Correct? Okay, at QP equal to infinity, we all know that it touches the j omega axis. Yes, but what about values less than QP? It is complex, that we know already. Alright, I will give you a clue. Please look at the, can you look at the location of the poles and find the magnitude of the complex number? The poles are complex quantities. What is the magnitude? It is a circle. You can see that the magnitude of the poles is constant, right? So, it is not parabola, it is not does some weird shape, it is very clearly a circle. You understand? So, as the q keeps increasing, the poles basically move closer and closer to the j omega axis, and as q tends to infinity, the poles will all right. Now, so let us say we have some for some q you have those two poles there, and again as a quick refresher, if you have a pole at if you have two poles at minus alpha plus minus j beta, right, what comment can you make about the impulse response of a system with poles at these frequencies? So, if you have poles at minus alpha plus minus j beta, the impulse response will contain components of the form e to the minus alpha t some cosine of beta t plus some phi, okay, where that phi and the magnitude of this whole thing depends on other poles and all this other stuff. But this is the natural frequency that corresponds to a pole at corresponds to poles at minus alpha plus minus j beta, correct. So, in our case, therefore, in our example, poles here will correspond to e to the minus transient response, which contains components e to the minus omega p times t over 2 q p times cosine. For large q, what comment can you make about the imaginary part? What can we neglect? 1 by 4 QP. I mean, for example, if QP is, I don't know, 5, 1 over 4 QP square is 100. So, square root of 1 minus 1 by 100 is 0.995, right. So, basically it is pretty much omega p. So, this is approximately some omega p times t plus some phi. Does it make sense? Alright. So, for large q, what comment can you make about this that waveform? I mean, how will this waveform look for large q? For infinite q, sustained oscillation. For for large q, it will take a large time to decay, right, and for very small q it will decay fast, right. So, basically the transient response will contain some kind of the impulse response therefore will contain some kind of component like this, where the decay of this envelope depends on q. So, the larger the q, the longer it will take for the envelope to decrease, right. So, therefore, if the impulse response contains something like this, what happens if you have a step to such a system with a large q? Let us say this is a step. How will the step response look? Yeah. So, basically there will be a lot of overshoot and lot of ringing, right. It will take forever to die. Okay. Now, when you have an amplifier, do you think this kind of step response is desirable? Yeah, I mean such a response may be desirable in other situations, but definitely not for an amplifier. Okay. So, a ringing step response is definitely not desired in an amplifier. And and the classic example I can give you for this kind of ringy response is let us say you are traveling in a bus, okay, and the shock absorbers are messed up, and you are sitting in the last seat of the bus, and the bus goes and hits a pothole, and what do you keep going up and down, right? And before you go, before you are manage to come to rest, the bus hits another pothole, and therefore you will keep jumping up and down like that, right? And so this goes on forever, right? So there is definitely not, that is a case where the system's Q, the quality factor of the natural frequencies of that mechanical system are very, the quality factor is very, very high. Okay. Whereas if you fix the shock absorbers, what is it doing? It is basically making sure that the quality factor is low, so that the response does not have ring. So, so high quality factor is not desired. Now the question is, okay, well, high Q is not desired, so maybe perhaps low Q is desired. So what about low Q? If I make Q much smaller than half, then what will happen? Yeah. So basically, if Q is very small, then for all practical purposes you can neglect this. I mean, if Q is very small, then this 1 over Q is very large. So for all practical purposes you can neglect that S square by omega p square, and this looks like a single pole system with so let us say I have an equation 1 plus x equal to 0. What are the roots? X equal to minus 1. Now if I add 0.0001 x square, how many roots are there?